Okay, this video is going to be an introduction to PyTorch. It will assume a little bit of background knowledge on machine learning, things like what is a neural network, but you can go ahead and check out some other videos on this channel for that. But if you don't have any PyTorch experience, we're going to start completely from scratch in this video. I won't lie and say that this video covers everything you need to know about PyTorch, but it will give you a pretty solid starting point. So let's just get into it. First thing I want to say is that these two import statements right here are incredibly powerful. As a data scientist or machine learning engineer, or even just for side projects, PyTorch is almost the only library you'll need. Sometimes you might use pandas for loading in certain data sets, but you can pretty much get away with exclusively using PyTorch. So learning this library is extremely high ROI. And the fundamental concept behind this library is the idea of a tensor. You might have heard of something called TensorFlow. PyTorch is kind of like the industry standard now, especially in research, but it was actually used for ChatGPT. But so TensorFlow isn't used that much anymore, but the fundamental data type in PyTorch is still something called a tensor. And a tensor is kind of just like a matrix or an array. We can have one-dimensional tensors, two-dimensional tensors, three-dimensional tensors. We can have like a 3 by 10 by 20 tensor, which you can think of as 3 different 10 by 20 matrices or arrays or tensors. And these store any kind of data we wish, usually integers or floating point numbers, but they can store any kind of data we wish. But tensors are actually more than just a matrix or an array. They carry derivatives under the hood. So you never have to thankfully worry about doing derivatives by hand with PyTorch. That's the amazing thing. You don't have to be bogged down by doing derivatives by hand or linear algebra or matrix multiplications by hand, because this library, this goated library, and these two import statements take care of the ugly math for you. And as a result, with this main data type in PyTorch, this main data structure, it carries various derivative attributes associated with it that you never really need to access or look at, or it's extremely rare that you would need to. But we should know that this tensor data type carries other information and other properties that are used to calculate derivatives actually inside a directed acyclic graph inside PyTorch under the hood. So we should know that tensors are more than just matrices or arrays, even though we're going to abstract them away to essentially be as such. So why don't we create our first tensor? We can just say that a equals torch.ones. This is a function within PyTorch that can take in a variable number of arguments. So depending on what we want the dimensions of our tensor to be. So if we wanted a 5 by 5 tensor, we would pass in 2 arguments. And if we run this, we can actually go ahead and see that tensor. Just go ahead and print it. We can go ahead and see that tensor. And here's our 5 by 5 tensor. And we can actually, although it's not necessary to, access other properties like the gradients or the derivatives for this tensor. Since we haven't done anything yet, there wouldn't actually be any information on that, but we should know that that information is there, stored by PyTorch under the hood. So now that we've created our first tensor, why don't we jump into some of the most important functions in PyTorch that involve tensors. Okay, so one of the first most important functions in PyTorch that we'll deal with is something called the sum function and the mean function. So we might say something like sum equals torch.sum, and it will have 2 arguments, the tensor and the axis or dimension along which we want to sum, right? So we might say something like a, and then axis, because we have a 2-dimensional tensor here, the axis will either be axis equals 0, or we might say something like axis equals 1. And this essentially is going to specify whether or not we want to sum along the rows or the columns. However, one important and maybe unintuitive thing is that if you wanted to get the sum of every row, we have 3 rows in this tensor right here. It's not this. If you want to do torch.sum of a, axis equals 0, you might think that axis equals 0 corresponds to rows and axis equals 1 corresponds to columns. So to get the sum of every row, you would say axis equals 0. It's actually the opposite in PyTorch for some reason. Not sure why this was done by the creators of PyTorch, but it is an important thing to know, as you'll be specifying axes all the time when you're working with PyTorch. So to get the sum of every row, what we actually want to do is go across the column. So that's why we say across the axis equals 1. And if we go ahead and print this, if we go ahead and print sum, we should actually get the sum of every row. And we can see the sum of every row is 5. So this is definitely an important concept in PyTorch, the concept of axes. Another important concept in PyTorch is the idea of squeeze and unsqueeze. This actually happens, these are two functions that are used all the time in PyTorch. And they happen when we have kind of unnecessary dimensions. So we can just kind of erase this for now. We can say our tensor that we care about right now is a 5 by 1 tensor, right? So 5 rows and 1 column. And if you were to like do print a.shape, you would get a tuple which has 5 in the 0th index and 1 in the 1st index. But that 1 is kind of unnecessary, right? The whole point is that, like, if we print a, it's just, of size 5 or of length 5. This whole saying 5 by 1 and saying, oh, it's just of size 5 is kind of carrying the same information. But when we're using other functions later on in PyTorch, some of these functions are really particular about if we're talking about a 5 by 1 or just something that is of size 5. Sometimes you might see this notation in PyTorch, the comma, which indicates that it's not 5 by 1, it's just of size 5. So if you want to ever get rid of the 1, there is something called squeeze in PyTorch. It kind of squeezes out any unnecessary dimensions. So if we were to say print a.shape, right, and then we were to say, okay, squeezed equals torch.squeeze on a, and then we print squeezed.shape, we will actually see a difference, right? The 1 has now disappeared, and although this might seem like an extremely small change, it will actually make a difference for various functions that we use later on. Just to make this kind of really clear, let's print a when it's 5 by 1, and let's print squeezed. We can actually see that there is a difference, right? Here we can see in the first tensor that there are 5 rows and 1 column. This is just simply, you can think of it as a vector of size 5. We've kind of erased a little bit of information about its dimensionality. So squeezing is important. So if squeezing is a thing, unsqueezing should also be a thing, right? Because sometimes we actually are passing into a function later on that expects 2 tensors, right? And we want things to be consistent with those 2 input tensors, right? We can't have 1 tensor pass into this hypothetical function that has this extra 1 and 1 that doesn't. So unsqueezing might be something that, it actually is something that is done all the time, and it's just like a good function to be familiar with. So it might say something like unsqueezed equals torch.unsqueeze, and you have to pass in the first thing, which is what you actually want to unsqueeze. So that would be squeezed. But then you actually have to specify dim, and dim is just like axis. In this case, it is essentially where do you want to insert that extra dimension. So I can say, well, it's currently of just size 5, right? To make it 5 by 1 again, right, I would have to say dim equals 1. Because at the 0th index of the shape, right, if we were thinking of a tuple of size, if we printed the shape, it would actually be, why don't we do that? That's probably a good practice. So let's print squeezed.shape. And this is how you get the shape of any tensor in PyTorch. We don't need these. Let's just print squeeze.shape. It's just going to be essentially just a 5, right? But we want to make it 5 by 1, right? So we want it to be like a comma after this 5 and then a 1, right? So that's kind of the 1th index in this iterable or this data structure that is returned by shape, right? If we just get the 0th index in shape, we see that it's 5. If we tried 1, it would be out of bounds, right? So to unsqueeze, we simply want to add this 1 to make it 5 by 1 at the 1th index of the shape. And now if we print unsqueezed.shape, we can see that we have it as a 5 by 1 now. So it's very important to be familiar with squeezing and unsqueezing. How do we actually define neural network models in PyTorch? Because that's what this library is all about. PyTorch is all about defining models that are specifically neural networks. So we have this rough idea of a model, right? It should be some sort of class, probably. Let's just call it my model for now. And maybe there is a constructor where we initialize the various objects that are going to compose this model. This might be the layers of a neural network, as we previously talked about. And there's one core method that is really important for models. And it's always called the forward method, which is really similar to something called get model prediction, which If you're not familiar with my previous videos, that's okay. But get model prediction, just kind of by the name, is essentially a method that would use the model. It would send in, so this would actually send in some example data point, right? This is essentially a subroutine where you could send in an example data point and the model would use whatever weights and biases that it currently has after, some number of iterations of training, and it should return the model prediction. So for a model object, the main ideas are a constructor and a forward method. And to make kind of this whole process of defining these neural network models much easier, PyTorch actually has a base class, which we can view over here. And this is an incredibly important concept within PyTorch. It's the idea of a module. A module is basically the same thing as a model. And all neural network models that you define in PyTorch are going to inherit from or subclass a class called nn.module. So if you want to define your own module, class model, you just specify that it subclasses or inherits from nn.module. And then when you have the constructor, we're kind of defining the layers of the neural network. This model right here is actually using convolutional layers. It's a convolutional neural network. We haven't talked about those yet, don't worry about it, but it is essentially a layer within a neural network. And then, as we talked about earlier, the main kind of method that's important for neural network models, every subclass of nn.module needs to override the forward method from the base class. It's going to take in an example data point or set of data points, a batch of data points, x, and using the model, it is going to, using the layers of the model, and maybe some other functions, as we can see in this case, which we'll talk about later, we are actually returning the ultimate model prediction. That is what the forward method does. So this is nn.module, and why don't we kind of learn by example and create our own model. Okay, so now we need to talk about an extremely important existing module in the PyTorch library that we'll use as a layer in our neural networks all the time. And that is called nn.linear. If you're familiar with neural networks, you know that each layer of a traditional vanilla neural network is actually just a bunch of nodes that are each doing linear regression based on the previous layer's input attributes, right? And you know that the only things that you really need to specify are the dimensions of your matrix, right? Which is just going to be dependent on your current or output layer's number of nodes and the previous layer's number of nodes. And those are the only required attributes to pass in to nn.linear. The rest of these are actually optional and we don't need to worry about them for now. But to essentially create a layer of a neural network, specifically a kind of a traditional, fully connected neural network, all we really need to specify is in features and out features. And in features is essentially the number of nodes in the layer previous to this layer, right? That's essentially coming in to this layer. And out features is the number of nodes in this layer. So why don't we take a look at an example? If you just Google neural networks, this is actually one of the diagrams that comes up. So I think that a good way to kind of make this diagram less scary is we're going to implement this exact diagram in code. So just to make that super clear, this is our input layer to the neural network. Whatever data set we're dealing with here clearly has 1, 2, 3, 4 attributes associated with it. And then our subsequent layers, this layer, and this layer, are actually doing computation, right? They're figuring out the weights, the W's necessary to actually make the model give the right prediction. So we're going to have 1, 2, 3 instances of nn.linear in our model. And this is just going to be the input to the model. So let's go ahead and say class simple. I don't know if it's simple. Let's just call it my model. And we know it has to subclass nn.module. And the first thing we need is our constructor, right? So we'll just go ahead and create our constructor. And we'll say that there's not really any other attributes now that the user can specify when creating this neural network. We'll just hard code them to be whatever's in this diagram. First thing we'll need is our super call, just kind of boilerplate code. And now we need to start defining our neural networks, right? So in features and out features. So we can do self.first layer equals nn.linear. And in features is going to be 1, 2, 3, 4. And we can see that out features, or the number of nodes in this layer, remember each node is doing linear regression. We have 1, 2, 3, 4, 5, 6. So that's all we would do there. Then for the second layer, it's pretty self-explanatory. The out features from the previous layer should be the in features for this layer. So that would be 6, and if we count how many are here, that's obviously 6 as well. But whatever model this neural network was for some reason it's predicting 2 numbers, right? So we can go ahead and do something like self.final layer equals nn.linear of 6, and then kind of down project to a dimensionality of 2. So the final output of this model, again, we don't know what use case or data set this model was created for. We just grabbed it from Google Images. We're just trying to clarify how to code up neural networks. We don't really care about the use case here, but for some reason it predicts 2 numbers, this neural network. So we would specify out features as 2 over here, and that would be it. Now all we have to do is override the forward method. Every subclass of nn.module does need to do that. So we will define forward. It is an instance method, so we have self, and we'll just say it takes an x, which is some series of data points. And we know that each data point needs to be of size 4. It needs to have 4 attributes. That's what nn.linear expects over here. And now what we want to do is, actually what we're going to do is, since each linear instance is actually a subclass, every nn.linear is a subclass of nn.module, it too has a forward method. So we're just going to call, and that's already overridden for us. That's already written for us by PyTorch. So we're going to call the forward method from each of these linear instances. So we might say something like first layer output equals self.first layer, and we're calling the forward method from that, that instance of a linear class, which is a subclass of nn.module. So we will pass in x. However, something to make the syntax more concise in PyTorch is that the following also works to call the forward method. You can just pass in x directly like that, and PyTorch infers that you were calling the forward method from that layer. And then what we essentially want to return then, right, is just kind of pass in x to this layer. The output of this layer goes to the second layer. The output of the second layer goes to this final hidden layer, and then is passed and does some final computation, some final matrix multiplications to get our output over here. So we can just return self.final layer. Into that forward method, we want to send in self.second layer, right? And into the second layer, we want to send in self.first layer. And then we're simply passing in x into there. So we're in a chain here, kind of calling all the forward methods consecutively in a sequence. And this is our first neural network model. And one thing we should probably clarify is all the W's, right? The weights and biases, we haven't done any training yet at all, right? So if you check the documentation over here, it will actually say that the values, right, for the weights of this model, same thing for the biases, it's initialized from some kind of probability distribution. That's not super important for this video, but the point is that these initial weights that are hidden, we can't really see that. It's abstracted away from us. But the weights in the matrices that this model is currently using to make our prediction, they're initially just randomly chosen. So if I were to make an instance of this model right here, right? Model equals my model. Now I have an instance of this model, and I could technically use it to grab predictions of data points, right? So let's say our first data point, example data point, let's just say that it is 1/4. We're going to make it a 1/4 tensor. And the reason we're going to make it a 1/4 tensor is we just want to do a batch size of one single data point, and every data point needs to have 4 attributes. And we'll just send in like completely random numbers for a data point. So torch.randn is actually the function in PyTorch to do this. And we can just pass in 1, 4, 1, 4. And if we send this into the model, if I call model.forward of this example data point, but we know that for all subclasses of nn.module, PyTorch will infer which method we're using if we just do this example data point. If you just do this, what the model is going to do is it's going to pass this data point in from left to right through this network, doing all the matrix multiplications using our current weights of the model. But the weights of the model right now are completely meaningless, right? They were just randomly initialized from this probability distribution described over here. So if I was to do this model, send in example data point into the model. And if I was to actually print this, there's no point in really doing that right now. It would be completely uninterpretable, right? Because we haven't actually trained this model yet. So while we won't cover that in this video, the next step to do after you make an instance of your model is we need to train the model for some number of iterations. Then we can actually use the model and get predictions. So after the training step is done, kind of leaving this as a black box for now, it's going to involve calling various gradient descent functions from PyTorch, and that's absolutely something that we're going to cover in a later video. But after we train this model, then we can actually do all we want. We can keep using our model and kind of using it to see how good its predictions are. We can send in various example data points into the model. So this is an intro to PyTorch. We covered the various concepts behind a tensor and different basic functions associated with tensors. We actually wrote our first neural network model. We defined its architecture based on kind of a predefined architecture that we found from Google Images. And be sure to check out the practice problems where you will actually write your own model classes to do things like diabetes prediction, predict the next words in a sequence like ChatGPT. Then we will also have practice problems on training the model and using the model to get predictions.